This video lecture is meant to cover the information from Unit 15, Acids and Bases, and today we're going to be learning about neutralization reactions and titrations. Starting out with objective number 8, which says you're going to identify neutralization reactions, identify the acid, base, salt, and water molecules in a neutralization equation. A neutralization reaction, which is really just a double replacement reaction, is when you have an acid and a base reacting and in a reversible reaction to produce a salt and a water. So for example, an acid typically starts with an H and then it's followed by some anion. Let's call that anion X. The base is typically a cation, let's call that cation Z, followed by a hydroxide. So if you have an acid reacting with a base, what happens, it's a double replacement reaction, which means the cation from the first molecule will stick together with the anion of the second molecule. HOH then, of course, becomes the water. And what we see over on the other side is the cation from the base, the Z, will stick to the anion from the acid, and so you will have a compound that is known as a salt. And so, of course that's not Zn, that's Zx. Alright, so a salt and water are your products. And if this is a strong acid and a strong base, and they're exactly neutralized with each other, you will have a neutral set of products. Now there are some situations where the products, the saltwater solution, can be slightly acidic or slightly basic, but that's a topic for a different lecture. For our purposes, we have neutral products, salt and water, and the salt is the ionic compound that is produced as a result of mixing an acid with a base. All right, so if we have our first example here, we have hydrochloric acid and sodium hydroxide. And what we can see here is the H and the OH are going to link up together, and the sodium and the chloride are going to link up together. Always, make sure you're putting the cation first, NaCl, and the other product, of course, is going to be water. All right, let's take a look at example number 2. Here we have carbonic acid reacting with sodium hydroxide. All right, let's take a look. The H's from and there's 2 of them from the carbonic acid, are going to link up with the 2 hydroxides that are in the sodium hydroxide. So you're going to end up with 2 water molecules. And then we can see here the other things are going to be the Na and the CO3. Now, so this is going to be NaCO3, but you have to remember that when you are recombining cations and anions, sodium's a +2, carbonate's a -2, so you're going to end up with a formula of Na2CO3. All right, and that maintains our balanced equation. Let's take a look at the next example, HCl and NH4OH. This is hydrochloric acid and ammonium hydroxide. The H and the OH become your water molecule. And then the other combination, make sure you put the cation first, NH4Cl, they're both a +1 and a -1, so ammonium chloride is the salt that is produced. All right, so neutralization reaction, the acid and the base will produce a salt and a water. If you were to make this particular reaction in example number 3 take place, you would end up with a saltwater solution of ammonium chloride and water. If you allowed the water to evaporate, the salt that would be left behind is the NH4Cl, and you will see questions like that coming down the pike at you. All right, so let's take a look at this next section right here, which is the topic of titration, which covers objectives 9, 10, and 11. Objective 9 says, describe the purpose of an acid-base pH indicator and recognize the color changes in litmus paper and phenolphthalein. 10, explain how acid-base titration is used to calculate the concentration of an acid or base. And number 11, analyze the concentration of an acid or base solution using the titration equation. Ma times Va is equal to Mb times Vb. All right, titration is a lab technique used to determine an unknown molarity of an acid given a known molarity of the base, or vice versa. If you know the molarity of the acid, we can use this technique to find the unknown molarity of the base. Regardless, whichever molarity solution you know the concentration of, that is what is called your standard solution. The end point is when neutralization takes place. And you can tell this if you had a pH meter, but we're not going to be using pH meters, so commonly what we use is an indicator that changes color at neutral pH. And so typically we're going to use the phenolphthalein, the one that turns pink in the presence of, as soon as it turns basic. So we're going to tell that neutralization or the end point has occurred when the indicator changes color. The equation that we're going to use is the titration equation. Ma times Va is equal to Mb times Vb. And we're going to add something to this. We're actually going to have you rewrite this because to fit this in, we're going to change this to be Na times Ma times Va is equal to Nb times Mb times Vb. Okay? So let's defining all of this. Ma is the molarity of the acid. Va is the volume of the acid. And Na is the number of hydrogen ions in the formula. Okay. On the base side, everything's effectively the same. Mb is the molarity of the base. Vb is the volume of the base. This Nb, I'm going to put this down here. Nb is equal to the number of hydroxide ions in the base formula. Okay. So if we ignore the N's for the moment, I'm going to show you why this equation works. Molarity of the acid. Remember, molarity is moles per liter. And if you know the moles of the acid and the liters of the acid, and you multiply that by the volume of the acid that you need, what you get is the number of moles of acid. If we do the same process for the base side, if you know the moles per liter of your base, and you're multiplying it by the liters of base that you need to neutralize the acid, what you get is moles of base. So when you put these two, MAVA is equal to MBVB, what you have is moles of acid being equal to the moles of base. And when that happens, that's neutralization. All right, so that's why this equation works. Now, the note that it says here, if the acid has more than one hydrogen ion or the base has more than one hydroxide ion, be sure to factor that into the titration equation. That will be taken care of if you use the Na and the Nb. Okay, if you use those, it effectively, if you have two hydrogens or three hydrogens in this example, H3PO4, it has 3 hydrogen ions. So what that effectively does is it triples the molarity of the acid. The second example, magnesium hydroxide, has 2 hydroxide ions, so that effectively doubles the molarity of the base, and that would be factored into your equation when you use the N's. All right, let's try a few of these examples. All right, so let's try some examples with this titration equation. The first thing you can see, we have a problem that says we have a 0.15 molar solution of NaOH titrated against an HCl solution. It takes 20 milliliters of the base solution to neutralize 30 milliliters of the acid solution. What is the concentration of the acid solution? Well, the first thing you can ask yourself is identify what's the acid and the base. We see HCl as the acid. We see NaOH as the base. The HCl has 1 hydrogen and the NaOH has 1 hydroxide. So for this problem, we do not need to use the N's in the equation. Right? We're just going to use the MAVA equals MBVB. Identifying what's what. The molarity of the acid is what we're trying to find, and I know that because the question at the end says, what is the concentration of the acid solution? The volume of the acid is given to us here. We're going to neutralize 30 milliliters of the acid solution. The molarity of the base is given to us at the very beginning, 0.15 molar. And the volume of the base is given right here, 20.0 milliliters of the base solution. Okay, so solving for MA, we plug in everything else. Molarity of the acid is equal to 30 milliliters, is equal to 0.15 molar, and the volume of the base is 20 milliliters. Now you might be wondering whether or not you need to convert these volumes to liters, because that's what the volume is supposed to be measured in, and that's what would cancel with the volume in the molarity unit of moles per liter. But you can see here that when we divide both sides by 30 milliliters as we solve for the molarity of the acid, milliliters cancel, and so you're actually all set. So the molarity of the acid will come out properly because your unit's canceled, and 0.15 times 20 divided by 30 comes out to 0.1 molar. All right, we're going to limit that to 1 sig fig because our volumes had only 1 sig fig. Problem number 2. Let's take a look at our acid and our base here. We have KOH and we have HCl. Notice 1 hydroxide and 1 hydrogen, so we are going to not use the N's in the equation. So we're just going to start with the MAVA equals MBVB. And if we define what all of those things are, I'll erase that, make that look a little cleaner. The volume of the acid, the molarity of the base, volume of the base. It says 25 milliliters of a 1 molar solution of KOH. So those numbers are associated with the KOH, with the hydroxide, with the base. So our volume is 25 milliliters for the base, and our molarity is 1 molar for the base. It is used to titrate a 0.45 molar solution of HCl. So that's our concentration, our molarity, 0.45 molar. And what is the volume of the acid? So that's what we're going to find is the VA. So plugging in, the molarity of the acid is 0.45 molar. VA is what we're going to solve for. MB is 1 molar. The volume of the base is 25 milliliters. When we divide both sides by the 0.45 molar, the molarities unit will cancel, leaving us with milliliters, which will be how we express our volume. 1 times 25 divided by 0.45 works out to 55.5 milliliters. However, if we had to express this to 1 sig fig, because our molarity up here was in 1 sig fig, the molarity of the base, we would have to round that to just be 60 milliliters. So that's the best answer for number 2. Number 3, our acid and our base, HCl, NaOH. 1 hydrogen, 1 hydroxide, so we're just going to stick with the basic equation, MAVA equals MBVB. The molarity of our acid is what we're trying to solve for, because that's the question right there. What is the molarity of the acid? The volume of the acid, it says 0.250 liters of HCl. So that's our volume of our acid. The molarity of the base says, let's see, it's titrated to its endpoint with 0.010 liters of 0.200 molar NaOH. So the molarity is 0.200 molar. And the volume of the base is equal to 0.010 liters. So plugging our numbers in, we get molarity of the acid times 0.250 liters is equal to 0.200 molar times 0.010 liters. Okay, and I see here that if I go to divide by 0.250 liters, Liters will cancel. And I see that that just went off the screen, but the liters there cancel. And mathematically, what do we get? We get 0.200 times 0.010 divided by 0.250. What we get for the molarity of our acid is to two significant figures, 0.0080 molar. Number 4. What we see for number 4 is we have a, let me move this screen here. It's better. Our acid is H2SO4. So here we have an acid with 2 hydrogens, and our base has 1 hydroxide. So now we're going to have to use the equation factoring in the number of hydrogens. So Na times Ma times Va is equal to Nb times Mb times Vb. The Na, because there's a subscript of 2 after the hydrogen, that's going to be a 2. And the Nb is going to be 1. So we'll come back to this equation after we define our molarities and volumes. The first number I see is 40 milliliters of an 8 molar sulfuric acid solution. So the molarity of the acid is given at 8.0 molar. The volume of the acid is given at 40.0 milliliters. The molarity of the base is what we're trying to solve for, and the volume of our base is 240 milliliters. Okay, so plugging things in, the molarity of our acid is 8.0 molar. The volume of our acid is 40.0 milliliters. That's going to be equal to 1 times the molarity of the base, which is going to be what we're solving for, times the volume of our base of 240 milliliters. Okay. We're dividing everything by 1 and 240 milliliters. Milliliters cancel, and so the math becomes 2 times 8 times 40 divided by 240. All right, and our answer will work out to be, to 2 significant figures, 2.6 repeating molar. Question number 5. We have HCl as our acid, NH4OH, ammonium hydroxide, as our base. That's a 1-to-1. It's 1 hydrogen, 1 hydroxide, so we do not have to worry about our N's. So molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Defining what everything is, we have 50 milliliters of a 2.0 molar HCl solution. So that's 50 milliliters is the volume of our acid. The molarity of our acid is 2.0 molar. It is used to completely neutralize 20 milliliters of our ammonium hydroxide solution. So we know the volume of our base. What is the molarity of the base solution? Okay, so plugging everything in, we have 2.0 molar times 50 milliliters is equal to the molarity of the base times the volume of the base, which is 20 milliliters. Dividing everything by 20 milliliters. Milliliters cancel. We didn't have to worry about adjusting any volume units. The molarity of the base, we should really have only 1 significant figure in our answer. 2 times 50 divided by 20 gives us 5 molar. Number 6, we have a 0.15 solution of NaOH. It is used to titrate a 0.128 molar solution of H3PO4. 38.5 milliliters of the base was necessary to completely neutralize the acid. Calculate the volume of the acid required to neutralize the base. All right, because we have NaOH, that's a single hydroxide, but we have 3 hydrogens in our phosphoric acid, we are going to have to use the N's in this equation. we see that we're going to use a 3 for the number of acid protons, but the number of base hydroxides is just going to be 1. So let's go over here now and define our molarities. The first number, 0.15 molar solution of NaOH. That's the molarity of our base. It is used to titrate a 0.128 molar solution of the acid. So the molarity of the acid is 0.128 molar. 38.5 milliliters of the base was used. So we're solving for the volume of the acid. So molarity of the acid, plugging it in, 0.128 molar, times our X, which is the volume of the acid, is equal to, let's see, the molarity of the base was 0.15 molar, and the volume of the base was 38.5 milliliters. We're solving for VA, so we have to divide by 3 and 0.128 molar. All right, so the 3's cancel, the 0.128's cancel. We have VA is equal to this. Well, molarities cancel, and so 0.15 times 38.5 divided by 3 and divided by 0.128 again, rounding our answer to, let's see, probably 2 significant figures. We should find out that this works out to be 150 milliliters. All right, challenge question. We've got a 10.00 milliliter sample of sulfuric acid from a battery. It requires 32.74 milliliters of a 2.15 molar sodium hydroxide solution for complete neutralization. What is the molarity of the sulfuric acid? Well, since we see in this equation there are 2 hydrogens in the sulfuric acid, there's 1 hydroxide in the NaOH formula, but because of those 2 hydrogens in the sulfuric acid right here, that's where we're going to have to factor in our N's. So Na times Ma times Va is going to be equal to Nb times Mb times Vb. So we already know this is going to be a 2, and this is going to be a 1. All right, so let's define what we've got. The molarity of the acid is what we are solving for right there. That's how I know what is the molarity of the acid. The volume of the acid is given to us right away, a 10.00 milliliter sample of a sulfuric acid. The molarity of the base is given to us right here, 2.15 molar solution. And the volume of the base is given to us right here, 32.74. Okay, so plugging things in, the molarity of the acid is Rx. The volume of our acid is 10.00 milliliters. The molarity of our base is 2.15 molar. And the volume of the base is 32.74 milliliters. So when we're solving for Ma, we're dividing by 2 and 10.00 milliliters. So milliliters cancels. The molarity of the acid is going to be 2.15 times 32.74 divided by 10 and divided by 2. We're limited to 3 significant figures. The N's are an exact count, so we're not going to use those as our limiters, this 1 here and this 2 here. So you should find that you get a molarity of 3.52 molar. All right, that's it for neutralization and titration, and this concludes the new information in Unit 15. All right, we'll see you in the classroom.